So, after the exam, this first exam is going to be the same thing that is going to be on the final for like the first section, right? So, if we didn't do as phenomenally as you would have hoped for, if you do well on the first section of the final, right, I'll average those two scores of that section together, right? So, the first section is engineering fundamentals and material balances. Right, so we should all feel comfortable with reacting systems, non-reacting systems, unit conversions. That's basically the first concept stuff that we talked about. Now we're moving on to the next chunk, which is going to be thermodynamics focused. Right, but this is not the same thermodynamics you've seen already. Right, this is the thermo that you're going to be seeing next year. But in this class, we're not going to go over the theory of how the equations are derived. We're just going to talk about how to apply them. Right? So what we care about is multi-component, multi-phase equilibrium thermodynamics. And that's a mouthful. But basically what we're going to use this information for is to say, okay, under what temperature and pressure is our system going to undergo a phase change? What is the composition of the vapor phase going to be? What is the composition of the liquid phase? How much of the vapor phase do we have? How much of the liquid phase? So this makes it easier so when we're designing a flash separator or some other type of separator, I don't have to say, oh, it's 10% composition of the vapor stream. No, you can calculate what the composition of the vapor stream is. So what we're going to be talking about is the application of the theory that you're going to develop next year in Thermo 2. But we have to sort of get you a base level to help you solve problems. So the first thing that we're going to talk about, which is one of the most important properties for phase transitions, and most chemical engineers, we deal with liquids more often than anything else. Right? We do a little bit of solid handling, but for the most part, we deal with liquids and fluids. So the liquid-vapor transition is the best tool that we have to do separations. That's what a distillation column uses to separate things. Compounds that are more volatile, that want to boil easier, those are the ones that come out of the top of the stuff, or the top of the distillation column. The ones that are heavier or more difficult to boil are coming out of the bottom. Now the property that quantifies how easy or difficult something is to boil is called the vapor pressure. So the best way to explain the vapor pressure is using a phase diagram. Now we have drawn these PT phase diagrams before. All right, here we are. What phase? Solid, liquid, vapor, triple point, critical point. The vapor pressure is this line right here. And typically we write it as P star, and then we put in parentheses T. Now this doesn't mean it's pressure times by temperature. We write it this way as sort of a reminder, because this curve is an exponential function of temperature. So it's a very strong temperature dependence. So this little note that we keep to ourselves, this is to remind us that this is a function of the temperature, especially for when it comes to degrees of freedom analysis. Now one thing that we'll be talking quite a lot about in thermodynamics. In thermo, you have pressure, you have temperature, you have specific volume, you have enthalpy, you have internal energy, entropy. We got basically everything. Okay? The key thing to remember in thermodynamics, and which carries over here to this notation because we're not strictly a thermo class, every single one of these thermodynamic variables is a function of every single other thermodynamic variable, right? So according to the Gibbs phase rule, you basically need to assign two variables to fully define a single component system, right? So that means you could define U and S, and that only would exist at a given P and T. So it seems a little bit counterintuitive that the pressure and temperature would be a function of U and S, but in thermodynamics, everything is a function of everything else. So since we're not a thermo class, we write this P with T in parentheses to remind us that the vapor pressure is a function of the temperature. Okay? So that's what this notation here is for. And indeed, this is an exponential function. So what happens is that when P star is equal, when the vapor pressure is equal to the system pressure, does anyone know what happens when this occurs? Phase change. What do we call that phase change?
Well, it depends on which direction it's going.
Which of the two directions? Boiling and condensation, right? This is when a fluid will boil or condense. So if this is the phase diagram for water, right, and this right here, let's say, is 1 atmosphere. What temperature is this here? 0 degrees C. Okay? What temperature is this here? 100 degrees. So if I want to boil water, what I can do is I can take an ice cube and I can heat it up until it reaches 100 degrees C. Now that property is that, what we're saying here is that at 100 degrees C, the vapor pressure is equal to 1 atmosphere. But let's say, for example, I start off right here at 25 degrees C. I have to go down, and at about 25 degrees C, my P star at 25 is equal to about 3 kilopascals. So if I want to boil water, I can either lower the system pressure to around 3 kilopascals, or I can heat up the fluid until its vapor pressure matches the system pressure. Right? So I can either change the pressure of the system, or I can change the temperature of the system to modify the phase of what's happening. Right? So the vapor pressure here tells us an important information about how volatile the fluid is. Now what we're talking about today is just one liquid phase and one gas phase. Or sorry, rather one liquid component and then a gas phase. But what happens when you have two liquids with different volatilities? One of them will evaporate more than the other one will. And we have to work out the math of how that's going to occur. Okay, so that's vapor pressure. Now, one equation that you will hear about a lot next year is the Clapeyron equation. So the Clapeyron equation says that d dP star dt, this is the slope of the vapor pressure curve, right here, that we've drawn here. So this is, if I were to draw this out, this here, the slope, this is dP star dt. This is equal to the entropy change upon vaporization divided by the volume change of vaporization, or the heat of vaporization divided by T delta V. So again, we don't have to know the derivation, but we have to know how to apply these equations. So what's commonly done for most of the calculations that we'll be dealing with is we'll say that the vapor is equal to an ideal gas, and that the volume of the vapor is much, much greater than the volume of the liquid. Right, to calculate this delta V. So in which case, let me just write this out. So delta V of vaporization is going to be equal to the specific volume of the vapor minus the specific volume of the liquid. Right? That's how much the volume of the system changes when you boil it. And if we assume ideal gas behavior, equals to RT over P. So if we substitute this expression into this equation here, we derive what is called the Clausius-Clapeyron equation. Let's put this right, Claus. Okay. There's a reason why I'm showing all this. So the Clapeyron equation, this is something we can derive for any general phase transition, and hopefully you will see this next fall in your Thermo 2 class. If we simplify the expression, this is a general one, this could be for solid-liquid transition, whatever kind of transition you want. But if we simplify it down for a gas-liquid transition at low pressures, where the ideal gas law applies, we can derive the Clausius-Clapeyron equation. Now, there are a couple key things I want to point out here. Can we think of a function in calculus where its derivative has the function in it? Oh, sorry, let's put P star here. Change it out. Can we think of a function in calculus where its derivative also has the function in it itself?
Yes.
Sorry, I didn't.
Exponent.
Exponent. There we go. The pressure is an exponential function of temperature. And this is sort of a fundamental, innate, built-in property of the vapor pressure. The other thing I wanted to point out here is these two equations are exactly equivalent, but this is something you'll see pop up on occasion, especially in thermodynamics, where you take the function over here and you lump it into this logarithm. So you see this weird d ln p type expression. Right? That's because the derivative of the natural log is 1 over, and so it just works out sort of that you can kind of combine it there. So this is a common little trick that you'll see, but not oftentimes explained. But these two are exactly equivalent. So if you were to integrate these expressions, what you'll get is that the natural log of P star at some T2 divided by the vapor pressure at some T1 is going to be equal to related to the heat of vaporization right? We see we get some sort of an exponential looking function here, right? Because you have to take the exponent of this side to get rid of the natural log, right? And we can see that the vapor pressure is an exponential function. Now, why this matters?
Is that a negative for the HVAC, or is that just on?
It is a negative.
Okay, sweet.
Let me make it more clear. So, as with all of the other property data that we've talked about in class, the best, most accurate way is looking it up. If someone's actually measured it and looked it up, okay? For vapor pressure, there's an equation that you will be very, very familiar with called Antons Equation. So in the Felder book or any thermodynamic textbook, you will see a table of coefficients. So you'll have a function that will look like this, natural log, or it could be log base 10. Different books have different formats. I think the Felder book might use a log. So this equation, Antons equation, this is a correlation, right? It's kind of a semi-empirical function. These A, B, C, and then this T is temperature. It's a correlation. So that means that the units of the pressure that it tells you that the correlation is in, you have to use those units. The units of the temperature that it tells you the correlation is in, you have to use those units. But the key feature about it is it has exactly the same exponential form as what is theoretically predicted based on fundamentals of thermodynamics. So it is a semi-empirical fit. These A, B, C coefficients, they are a way to take basically a large table of temperatures and P stars, right? So imagine if you had real data, you'd have temperature, and you'd have P star, right? And you'd have all a bunch of listings here, right? Just like you do for enthalpy or internal energy, looking at steam tables. So instead of having a giant table, we condense all of that down into ABC coefficients. So it is slightly less accurate, but it is pretty accurate because it actually has a semi-reasonable functional form. Right? This is an equation you will all be very, very familiar with. But just key thing to keep in mind, whatever units it tells you the correlation is built in, you have to use those units. And whatever units it spits out, you have to use those units. So these A, B, and C coefficients, you could in theory back calculate and figure what the units of them have to be in order for everything to cancel out. Right? But just keep in mind that use these units that they tell you in the charts. And different books will have different units. And different tables will. Yes?
A little while ago, you said that the natural log was a transcendental function, right? Why is there units then inside of the natural log in that equation?
In this case, magic, since it's an empirical fit. Right? There's no theoretical basis for this equation other than the form of the function itself. So if you wanted to be super strictly mathematical about it, you could say something like over P star naught, where P star naught is equal to whatever the pressure units are of 1. So oftentimes you'll see that. So if you really want the units to work out precisely, you have to sort of do these little tricks. But in general, in this case here, since it's an empirical fit, you kind of throw those rules out the window. There's no functional basis for this other than the exponential aspect of it. But some of them will have natural log, some of them will have log base 10, so just key things to keep in mind. But the main point is that vapor pressure is a strong function of temperature. So if you want to change the separation characteristics of a process, changing the temperature has a massive impact on it. Changing the pressure will. So what we'll be doing now moving forward is I'll be giving you the temperature and pressure. Let's say, oh, your fluid's entering a separator at this temperature and this pressure. We'll be applying the thermodynamics that we're going to be talking about today and tomorrow or Wednesday, and you'll be calculating outlet compositions. But it also works backwards. Right? I could tell you what the composition of the outlet needs to be, and then you have to solve for the temperature or the pressure. Right? And so that's where problems get a bit more complex. All right. So that's vapor pressure. We'll be talking about it at the end of class. But for now, quick detour to some other concepts. The Gibbs phase rule. So the Gibbs phase rule tells us how many variables we need to define in order to calculate the compositions of vapor and liquid streams, or any sort of phase change process. This tells us the number of intensive variables intensive versus extensive variables. What is an example of an intensive variable?
Pressure and temperature.
Bingo. Temperature, pressure, mole fraction. These are all intensive. They are independent of system size. For most thermodynamic calculations, we perform them on infinitely sized systems. So that's why we care about the temperature, the pressure, and the composition. The size of the system that you calculate in thermo only comes through when you do a material balance. But in general, all thermal calculations are infinitely sized. That's sort of the general assumption that is made when you actually do thermodynamics. So intensive variables, as opposed to extensive like mass or volume, right? Intensive variables are what we need to focus on when we do our thermodynamics in this class. Right? What is the temperature, the pressure of the system, or what is the composition? And now moving forward, we'll be differentiating between y's and x's. Right? Y's are going to correspond to vapor mole fractions, and x's are going to correspond to liquid mole fractions. Prior to this point, we kind of reserved y's for mole fractions and x's for mass fractions. But in thermodynamics, the masses don't matter. It's only moles. Only moles matter for thermodynamics, right? So y is going to be vapor mole fractions and x's are going to be liquid mole fractions. This is the convention we are going to use from here on out anytime we talk about a multi-phase system. Okay, so the Gibbs phase rule tells us that the number of degrees of freedom that we have to define in order for us to know what is the amount, what is the phase and what is the concentration of each phase is equal to 2 plus c minus pi, where c is equal to the number of components and pi is equal to the number of phases. So let's look at an example. Let's see. Okay, let's look at an example. Let's say we have water in a container with a vapor and a liquid. So we have 2, that's the same, plus number of components, which is 1, minus the number of phases, which is 2. So our degrees of freedom are equal to 2 plus 1 minus 2, which gives us 1 degree of freedom. Meaning that if I want my water to exist in both the liquid and the vapor phases, I can only change one thing at a time. That could be either pressure or temperature, or the most common variables. In theory, you could change anything, but pressure and temperature are the most common ones that we're going to look at. That exactly corresponds to that vapor pressure curve. I cannot independently vary the temperature or the pressure. I have to vary them together if I want to stay in equilibrium here with 2 independent phases. Right? So pressure and temperature are linked together intimately in everything that we're going to be talking about from here on out. Now let's do another example, the triple point. Okay, so if we look at the triple point, our degrees of freedom is equal to 2 plus 1 component minus 3 phases gives us 0 degrees of freedom. We cannot modify, move, or manipulate the triple point. It is locked in space. I cannot vary it. So the Gibbs phase rule tells us this information. But the key thing that'll simplify a lot of thermodynamics, especially for multi-component systems, is to commit that every single thermodynamic variable is a function of every other thermodynamic variable. They're not like independent knobs that you can control, right? And this is what we learn here by looking at this process. If you want to change the system conditions, you only get to change a limited number of variables. So for us, pressure and temperature are the ones that we can most easily measure. But in theory, right, if we look at our list here of thermodynamic variables, let's say we had an enthalpy meter. In theory, we could redo everything that we do in chemical plants based on H and S. But the problem is we don't have a good way to measure H and S. We have a really good way of measuring pressure and temperature, so those are the variables that we predominantly use. But in theory, mathematically, we could control everything in our lives using any number of thermodynamic variables, right? That's the key thing to take away. All right. Now, on to sort of the meat of what we're going to be talking about. So far, these are kind of just more definitions. Let's work on actual practical problem solving. So right now, what we're going to be talking about is liquid vapor equilibrium. And I will oftentimes write this as LVE or VLE, vapor liquid equilibrium. Right, LVE, VLE. Write that down like VLE. So right now we're going to simplify, and we're going to start off with what they call one condensable component. So what this means is you have one liquid plus many, one liquid but many potential gases and liquids. An example of this is water evaporating. This is a simplified version. On Wednesday, we're going to be talking about multiple liquids and multiple gases. That's a multi-component, multi-phase. So for an example, we could say that this is water as our only liquid, and that your gases could be air plus water. Right, this is an example of a one condensable component. But it doesn't have to be water, right? It could be gasoline and gasoline plus air, right? But water is the most common one we'll be looking at. So if you look at our Gibbs phase rule, our degrees of freedom, we have 2 plus the number of components, which is how many? 2. Air and water. Water is in 2 phases, but there's still just 2 components. Minus the number of phases, which is 2. We have a liquid phase, and we have a gas or a vapor phase. That gives us 2 degrees of freedom. 2 degrees of freedom. Right, which means that we can either define the composition of the vapor phase and the pressure, or the pressure and temperature, or the pressure and the composition. Right, that gives us a couple tools that we can use to look at what's going on. So the equation that we will use to solve these types of problems is going to be something called Raoult's law. Who has heard of Raoult's law? A few folks. So this is a simplified version of Raoult's law, or called one condensable component. This is Raoult's law for one condensable component. I'm going to walk us through it. P of I, this is called the partial pressure. This is the pressure that is exerted on the surroundings only from species I in the system. We define the partial pressure, that's what these 3 equal sign means, as the mole fraction of that species times by the total system pressure. Raoult's law for one condensable component tells us that that is directly equal to the vapor pressure of species I. Now the full version of Raoult's law will be YIP is equal to XIPI star T. So in the full version, for every species, you have to balance out the composition of the vapor phase, which is the Y, times by the system pressure, which is equal to the liquid phase composition times by the vapor pressure. Now the simplification that we are doing here in the one condensable component is we are saying that no matter how many things we have in this system, only one of them can condense into a liquid. So in the case of water and air, air cannot condense to a liquid because it's a supercritical fluid. Right? Supercritical fluid means it's above its critical point, so no amount of pressurizing it will ever get it to turn into a liquid phase. It's always going to be a gas or a supercritical fluid unless you drop its temperature. So the air, I cannot make liquid air just by pressurizing it. I have to cool it down as well. So in this case here, I can never have air in the liquid phase because it's supercritical, so that this x of I goes to 1 because it's pure water, or close enough to pure water. So this full version of Raoult's law then gets simplified to the one condensable component. So how we know what 100% humidity is in terms of the mole fraction is based on this Raoult's law expression. Any questions on that? And note that I use the notation where x's correspond to the liquid phase and y's correspond to the gas phase. So from this Raoult's law expression, I want to go through a couple of key points here. That expression, the Raoult's law expression, is only valid at equilibrium. So at equilibrium, the partial pressure of a particular component is equal to its vapor pressure. So that's how we know that, for example, if we're at about 100 kilopascals atmospheric pressure, if water has a vapor pressure of about 3 kilopascals, then 3 over 100 gives us its mole fraction, right? This is equal to y I p. So that means y of I is equal to pi star of t over p. This tells us how much of a particular compound can evaporate and go into the gas phase or the liquid phase. Right, so the ratio of the vapor pressure and the system pressure tells us what the mole fraction of that component is. Number 2, you can never get your vapor pressure higher than the partial pressure. This is what we would call supersaturated. So if you have more vapor in your system than the fluid can hold, it will condense into a liquid phase. So if I wanted to run a dehumidifier, right, I want to lower the humidity level of the air in my room. I can do it 2 ways. I can increase the system pressure, or I can lower the temperature. But once I hit this saturation curve, which is given by Raoult's law, right, once I exceed the amount of water in this system here, then it'll start to condense into the liquid phase, right? So this is a super saturated system if we're going above and beyond what Raoult's law will allow us to predict. but the opposite is okay. Right? So what this is saying here is that if your partial pressure is less than your saturation pressure, that just says you're not fully saturated. Now this would be relative humidity, for example. So if we were in Texas, right, and it's like 90% humidity in southeast Texas, right, that's still not fully saturated. The only time it's really ever fully saturated is when it's raining, right? And when it's raining, it rains because of this property here. You have more air in the atmosphere than the atmosphere can handle, and so it condenses into a liquid. Those are the rain droplets that then fall on us. In this circumstance here, this is like what's going on in Utah. Right? It's maybe 20% relative humidity. Right? We'll do the definitions of humidity right after we go through a few more points. But basically what this is saying is that in Utah, the air, according to its vapor pressure, can handle more than it has given. Right? So you can be underneath the Raoult's law prediction, but you can't be over the Raoult's law's prediction. Right? So in this case here, the Y of, let's say, water in air actually is less than the Y of water at saturation, where this star means at saturation. And saturation a lot of new concepts. If your mole fraction of water in air is less than the saturation amount, right, then you have lower humidities. Right? This is less than 100% humidity. Yeah.
Why you wrote superheated vapor? Does it have to be superheated?
Well, so the vapor that would want to condense is superheated. It's above. It's at a concentration. Let's go. If we kind of went back here a little bit. If you were to think about heating this system up here, you're far enough away from your saturation point that you could cool it down and you wouldn't condense anything. So anything that has that property, we typically refer to that as superheated. So in the case of the multi-component system, right, a good analogy would be, let's say we have a 100-degree day in Utah versus a 100-degree day in Texas. If I drop the temperature in Texas to 80 degrees versus drop the temperature here to 80 degrees, we would expect some water to probably condense as dew in Texas, but we wouldn't expect it to happen here. That's because the air here is much further away from its dew temperature or its saturation temperature than it would be in the case in Texas. Right? In Texas, you're really close to the saturation point. So any slight drop in temperature, some of the water in the air is going to condense. Right? But the key thing here is that Raoult's law does not predict the conditions that we always have. This is the maximum or equilibrium conditions. We don't have to be at this condition. Technically, equilibrium takes an infinite amount of time. So we're never going to be strictly at equilibrium, but we approximate it as such. But you can never exceed it. Right? So you can be lower than that prediction, but you can't be greater than it. And the last concept that I was going to try and talk about was basically the dew point, which was basically what we already discussed. So, as an example, so we can put this all together. I have a glass of water, and I put a little cap on it. Let's say the glass of water is sitting in the room at 25 degrees C, I can look up what are the properties of water at 25 degrees C. And let's just assume it's approximately 3 kilopascals is the vapor pressure of water at this condition. What we're solving for is what is the mole fraction of water at equilibrium. So an example of this is, let's say we're designing a chemical process to evaporate a glass of water. And so what you decide to do is maybe you decide to put in an air hose, and that air hose slowly bubbles. And the assumption you would make is that every air bubble that goes through the system is at equilibrium, which may or may not be true. Then the question could be, how much air do you need to bubble through the system in order to evaporate all of the water? Or another example would be a clothes dryer, right? How hot does the air have to be in your clothes dryer, and what is the volumetric flow rate of air such that it evaporates all of the water that's absorbed onto your clothing? But what limits how quickly you can evaporate it is given by the material properties of the system, of the thing you're trying to get rid of. Right? Let's say engine oil, right? Whoever's changed their oil in the car and they've gotten oil on themselves, it doesn't just evaporate, right? Because the vapor pressure of the oil is extremely low, right? It doesn't want to boil. But if you were to do this in a chemical plant or a refinery, you could easily vaporize that motor oil, right? But you'd have to heat it to maybe, what, 300-400 degrees C? Water has a much higher vapor pressure compared to a oil that you put in your car, which means it's a lot easier to evaporate, right? It'll just do it readily, just sitting on the table. So if we were to apply our Raoult's law with one condensable component, we're basically trying to solve for y by y of H2O is equal to, rearrange this expression, the vapor pressure of water divided by the system pressure. If this is 1 atmosphere, that means we have 3 kilopascals divided by 101.3 kilopascals, and we see it's about 3% water. Now let's say, for example, we were to look at this expression a different way. What if we wanted y to equal 1? If the mole fraction of water is 1, that means it's pure water. Under what circumstances does that occur?
When the pressure is equal to the atmosphere.
Exactly. This happens when P star, the vapor pressure, is equal to the system pressure. So we can change that by modifying the pressure of the system or by modifying the temperature. Right? Same way that you can boil water at room temperature just by lowering the pressure. Right? So if I had a vacuum pump and a bell jar, you could boil a glass of water. But I don't. Okay. The last few things that I want to go over, I won't have a chance to go over all of them, but I want to just hit on 2 key concepts. These are definitions of humidity. So generally, if we use the term humidity, this typically refers to water in air. So we use the term humidity specifically for how much water is in air, and that is because it's important because air is used in a lot of chemical processes, specifically combustion is a really big important one. The term saturation, for the case of Raoult's law with one condensable component, this can refer to any fluid in any gas, right? This could be benzene evaporating into neon, right? That would be a saturation condition. So the terminology we use, whether it's humidity or saturation, just typically depends on are you dealing with water or some other fluid. And this goes down to definitions. So we have a definition of relative humidity. Now this is the humidity you hear about on the news. We can also call this relative saturation. Right, so we'd use the term humidity if we're talking about the weather and how much water is in it, or we'd use saturation if we're talking about some tank of some other compound and something else. Right, this is defined as P of I, the partial pressure of species I, divided by its vapor pressure at the same temperature times by 100. So a 100% humid day corresponds to when the actual mole fraction of water is equal to its amount that would be predicted from Raoult's law. Right, so if you substitute in Raoult's law for both of these expressions, or the definition of partial pressure, you could also write this as y of I divided by yi star times by 100. So when the water in the air is at its 100% maximum limit, that is 100% humidity. If you have no water in the air, then you have 0% humidity. Right? But relative humidity is defined based on the limit at a particular temperature and pressure. Right? So relative humidity doesn't transfer exactly the same thing as, let's say, a material balance does. Right? You can have more water in the air even if the relative humidity is lower. It depends on the temperature of the air is. The next unit that you're going to be seeing quite a bit is absolute humidity. And again, we could also say absolute saturation if you're not specifically referring to water in air. This one is the mass of vapor per mass of dry air. But you could also come up with a similar system saying moles of vapor per mole of dry air. And there's a number of ways that you can write this expression here as well. But the concept of absolute humidity is that this is telling us if I have a kilogram of air, how much water is going to be in it. Right? That does not depend on what the temperature of the system is. The relative humidity depends on the temperature and pressure of the system. Absolute humidity does not. So some instances, this is the more convenient units. In some instances, this is. In terms of material balances, this is always what you want to go with. But in terms of our human bodies, we care more about relative humidity. Right? I don't really care how much water is in the air. I care more about how much water can I get to evaporate off of my skin. But if the air is 100% saturated, I have no incentive for that water to evaporate and cool me down. Right? So the relative humidity, in that sense, is more important. For material balances, this is almost always going to be more useful. All right, so please go to the schedule, look at the videos for the psychometric chart, TXY, PXY, diagrams, flash. Just watch all of them. You'll have a head start. It'll be a lot easier to learn the material this week. So please go ahead and do that, and have a good one. I'll post homework today as well.